Hi, I'm Maali Tars, and this is the presentation for the paper Extremely Low Resource Machine Translation for Closely Related Languages. There are a lot of languages that less than a million people still speak. And some of the languages have only a couple of hundred people still practicing it. In the neural machine translation context, this means that we have very little data available, especially parallel data and corpuses for training neural machine translation models. But we know that for training high-quality NMT models, we would need millions of sentence pairs, and this is why they are usually trained on high-resource languages like English, German, and so on. We, however, turn our focus on the extremely low-resource languages and try to improve the basic NMT approach to get acceptable and good quality NMT models for low-resource languages. In our work, we use the Finno-Ugric language family as an example, and we pick 5 of the languages: Finnish, Estonian, Võro, North Sami, and South Sami. Going forward, in the work, the experiments are all using the transformer architecture with tension mechanisms. So firstly, the main approach that we used was training multilingual models instead of bilingual models. We combine high-resource and low-resource languages into the same vocabulary and training space. That method is very beneficial for low-resource languages because they can learn from high-resource languages that have a lot of useful information about translation patterns. As we add the aspect of combining closely related languages, we know that the languages share a lot of lexical and sentence-level similarities. We use sentence space and byte pair encoding to tokenize the training data. And as we divide the training data into subwords using the byte pair encoding algorithm, we know that a lot of the word segments in the joint vocabulary overlap between the languages. Another method that we use is back translation, where we translate the monolingual data using the already trained multilingual baseline model, and as a result we get a new synthetic parallel dataset. Differently from the basic back translation method, we don't have to train a lot of bilingual models because we have the multilingual model that can train in 20 different directions, translate in 20 different directions. So for the data to become back translation, we reverse it. So the synthetic translations become the source side and the monolingual data becomes the target side. This assures that the model learns to translate source sentences into target sentences on correct target data. Because synthetic translations often contain a lot of flawed and inaccurate translations, and leaving them in the target data could hurt the translation quality. We also trained a transfer learning and a fine-tuning experiment for one of the language pairs, which we chose to be Estonian Võro language direction. And in the transfer learning experiment, we took the Estonian Finnish baseline model weights, and we initialized a new model with those weights and trained it on the Estonian Võro parallel data. In the fine-tuning experiment, we took the Estonian Võro parallel data that the multilingual baseline model had already seen, and we fine-tuned that baseline model on that same Estonian Võro parallel data. As expected, finding parallel data for the smaller Finno-Ugric languages proved to be very difficult. And it is worth mentioning that in our work, we define low-resource language pairs as language pairs that have less than 100,000 sentence pairs available. So in our work, Estonian-Finnish language pair acted as the high-resource language pair with 2.6 million sentence pairs, and other language pairs formed only about 3% of the whole parallel data set. We performed 2 back translation iterations, so that's why the monolingual data is in 2 sets. And parts of the monolingual data we collected manually from different files, especially for the Sami languages. We also used the downsampling technique, so we reduced the amount of monolingual data for the high-resource languages, Estonian and Finnish. That makes the low-resource languages more prominent, and the models should be more focused on learning about the low-resource languages. In the back translation iterations, we translated monolingual data into the other 4 languages equally. So, for example, from the 100,000 sentences of Estonian, 25% was translated into Finnish, 25% was translated into Võro, 25% into North Sami, and the last 25% into South Sami. The experiments in our work were evaluated with the Blue score, and we performed many different experiments with different data combinations and differences in initialized weights. We trained baseline models for all of the language directions, and the models were bilingual and one-directional. The next model in the graphic is the multilingual baseline model, and that achieved an average gain over the baseline models in the low-resource language pairs of about 7 points. You can see it in the black line in the graphic. And the best model averaged a gain of 9.2 points over the baseline models. The best back translation iteration models were trained on parallel data and synthetic parallel data, and were not initialized with any pre-trained weights. As mentioned before, we did a transfer learning experiment and fine-tuning experiment, and transfer learning experiment was even better than multilingual plus back translation models, having a gain over the baseline of about 11.9 points. Fine-tuning proved to be an even more effective technique because it achieved a 13 plus score gain over the baseline of Estonian Võro. Here is an example of a translation from Estonian to Võro, and we can see that the baseline model has totally lost the meaning of the sentence, and the best model fixes some of a mistake that the multilingual baseline model left in. But the best model still translates the word officially into a Finnish word rather than a Võro word. And we can speculate that this could be the result of combining 5 languages into the same vocabulary space and training them in the same encoder and decoder. Here's a demo of the best multilingual and back translation model that is being deployed on our university's NLP research team webpage. And we encourage everyone to go and use it. It's free, and you can translate text in all of the 20 directions that we offer. So in conclusion, we would say that fine-tuning multilingual models can achieve the best results, but it is not the most effective and compact way, because we can translate into 20 different directions with one multilingual model, but with fine-tuning we would have to train 20 separate models to achieve the same functionality. So in relativity, multilingual models plus back translation is a very beneficial method to get the best results for low resource languages in neural machine translation setting. But in the future we would like to research more about the fine-tuning of multilingual models, and also we would like to create a high-quality test set for all of the 5 languages. And here we would like to ask for some help from anyone who would like to help and who can help us translate in these 5 languages, especially for the Sami languages. And you can contact us on the Tartu NLP webpage. And I thank you very much for listening.